So in this example, we're asked to determine the relative errors in calculating the specific volume, specific internal energy, and specific enthalpy for liquid water at a temperature and pressure of 100 degrees C and 100 bar, that's an absolute pressure, respectively using the thermodynamic property tables and the saturated liquid state approximations. This is basically saying using the approximations for compressed liquids. So let's start first with determining these properties using the thermodynamic property tables. So we're dealing with a compressed liquid because we're told it's liquid water. So let's go to the compressed liquid tables. So those are given right here. And we're told that the pressure is 100 bar. So that's this pressure right there. And it's 100 degrees C. So the specific volume is right there. The specific internal energy is there. And there's the specific enthalpy. So let's go ahead and write those down up at the top here. So we just have to remember those numbers. So from the compressed liquid table, we have the specific volume is 1.0385 times 10 to the minus 3 cubic meters per kilogram. The specific internal energy was 416.23 kilojoules per kilogram, and the specific enthalpy was 426.62 kilojoules per kilogram. So those come directly from the compressed liquid tables. Those are the most accurate values that we'll have. Now what we want to do is use the compressed liquid approximations. So just a reminder what those look like. The specific volume of the compressed liquid at some temperature and pressure is about equal to the specific volume of the saturated liquid at that same temperature. The specific internal energy of the compressed liquid at the temperature and pressure is about equal to the specific internal energy of the saturated liquid at the same temperature. And the specific enthalpy of the compressed liquid at that temperature and pressure is about equal to the specific enthalpy of the saturated liquid at that same temperature plus, and then we need to do the pressure correction, the pressure that we're at minus the saturation pressure at the given temperature, and all that's multiplied by the specific volume of the saturated liquid at the given temperature. So just remember that for the specific enthalpy, the approximation includes a pressure correction term. Okay, so in order to evaluate this, we need to find the specific volume, specific internal energy, specific enthalpy, and the saturation pressure. These are all, the sub L ones are for the saturated liquid state. So to do that, we'll look at the saturated liquid vapor mixture table, which is this one. It's organized according to temperature, and we're particularly interested in the 100 degree temperature case, because that's the temperature we're looking at. Here is the saturation pressure at that 100 degrees. This is the saturated liquid specific volume, saturated liquid specific internal energy, and saturated liquid specific enthalpy. So let's remember those numbers. We'll come back up here and write them down. So the saturated liquid specific volume at 100 degrees C is 1.0435 times 10 to the minus 3 cubic meters per kilogram. The saturated liquid specific internal energy at 100 degrees Celsius is 419.06 kilojoules per kilogram. The saturated liquid specific enthalpy at 100 degrees C is, let's see, what's that one? That one's 419.17 kilojoules per kilogram. And the saturation pressure at 100 degrees C is 1.0142 bar. That's an absolute pressure. Okay, so now we have all the values we need here, which come from the saturation tables, to evaluate the calculations here. One other thing just to note is the pressure here will be 100 bar, absolute, whereas this saturation pressure is this one over here. One other quick thing you have to just be careful of is notice this is in bar. The specific volume will be in cubic meters per kilogram, so you need to do a little unit conversion here to make it work out properly. So just be careful of that. Okay, so then when we work these out, of course the approximation for the specific volume for the compressed liquid will be this value. The approximation for the specific internal energy will just be this value. And then to do the calculation for the compressed liquid approximation, that when you work that out, let me fix that, that's about equal to. When you do this calculation right here, that number comes out to be 429.50, I believe it is, kilojoules per kilogram, if I did my calculations correctly. Okay, so now that we have those values, so just a reminder, these are the ones coming from the compressed liquid table. Up here, these values are coming from our approximations. And then to find the relative error of some property is just going to be the value of the property, let's just call it P, coming from the approximation. Actually, it'll be the actual value minus the property value using the approximation, and then we'll divide through by the actual value. We'll just take the absolute value of it just to give us the relative error, just the magnitude of it. And so when we do that calculation, so what this is showing just what's the difference in the value of the property. P here is our property value. What's the difference between the actual value and the approximation, and then we just make it relative to the actual value. So this tells us how far off we are, relatively speaking, from the actual value. So for example, to find the error in the specific volume calculation, we take the actual there is this specific volume, the approximation is this value, and then again we divide through by the actual. And if you do that, you'll get the relative error for the specific volume comes out to be 0.0048, or just call it 0.48%. The relative error in the specific internal energy comes out to be 0.0068, or 0.68%. And the relative error in the specific enthalpy is 0.0067, or 0.67%. So those are the relative errors using our approximations. You can see they're all less than 1%, which means that these approximations that we're using right up here are very good ones. They're very reasonable to use for compressed liquids. If you use these approximations, you're only off by a very small amount just in general. Okay, we'll end the example there.